Hello and welcome to Algebra 2 with Mr. Clausen. Today I want to talk about solving real-world rational equations. And what I'm going to go over today is a simple jogging example and gardening example, but the main thing that I want to talk to you about in this video is how you can show work and show some of the relationships that are present within word problems. Because I know for some people, like, they can just look at a word problem, spatially analyze it, figure out some guess numbers to plug into a particular circumstance and just come up with the answer. And not to discredit that or to, penalize students for being able to intuitively figure that out is not something that I necessarily want to do, but at the same time, I think there comes to a point in mathematics that where the ability to go and identify relationships and then use those identified relationships to solve a problem is something that's really important. So you have to be able to write equations for these real world problems and then use those equations to go find an answer that you're looking for. Now, for some of you, it is really tough to start thinking about how to simulate those things. So I want to give you some pointers as far as how to lay this out in a table so you can start trying to find those relationships and then answer the questions that you have at hand. So let's get to the first problem here that I have, which is the jogging example. So in this jogging example, we have Rosa, and she can jog 5 miles downhill in the same time it takes her to jog 3 miles uphill. All right. And so from this question, I can see some really basic things as far as what's being compared here. Her ability to run or jog downhill, I should say, and uphill, respectively. And she jogs downhill 4 miles an hour faster than she jogs uphill. Find her jogging rate each way. Now, I will point out that this is a rate problem. I love rate problems. I think they're really simple circumstances that you guys can look at in terms of trying to figure out how to model them. And remember that rate is a form of a distance equation, which is just d is equal to r times t, distance, rate, time. And so now that I know that I'm looking at this specific type of circumstance, I know what a lot of my variables are, and I know what I'm comparing, which is jogging uphill and jogging downhill. And so what I'm going to do is I'm going to create myself a little bit of a table here. And what I'm going to do in the for my rows is I'm going to list out the things that I want to compare. So I want to be able to compare Rosa jogging. Let's go downhill and see how that compares to Rosa jogging uphill. So what I want to put here are things I want to compare. And again, this is just a technique, a frame of thought to start implementing so that you can look at this. And then what I want to include on the top here for each of my columns is I want to include things like my variables. So I want to include things like distance. I want to include rate. And I want to include time, since I've identified this type of situation. And as I mentioned previously, these are going to be my variables. And so that's how I like to set up these tables. And you will see tables set up in your textbook in the exact same way. There isn't any magical thing that they're doing here. We're just looking at what's being compared here and what are the variables here. And it's easy to add things or remove things, or if you're going through the question and then you're like, that is definitely easy enough to change. And I think this is worth points right here, to be honest. When you're looking at a situation, is being able to just say, hey, yeah, I'm comparing these two things and I have this, blah, blah, I don't know what to do with it beyond that. And granted, there wouldn't be a lot of points, but I think this is valuable just to be able to do this. So now what I want to do here is just start listing out some of the things that is listed out here. And what I see specifically is that Rosa can jog 5 miles downhill at the same time it takes her to jog 3 miles uphill. So she can jog 5 miles downhill and 3 miles uphill. Okay? Now, I don't include this as a rate because they're not giving us any amount of time. They're just saying same time. So that's all I'm going to say for now, because I think this is relatively pertinent information and something that we can take into consideration here. Now, rate is something that is, here, and we see that she jogs downhill 4 miles per hour faster than she jogs uphill. Okay, and so if we're comparing Rosa jogging uphill and jogging downhill, she jogs 4 miles faster downhill than she does uphill. So if we're looking at that rate, we know that the downhill rate is something like, let's put in a variable for now. Let's go R uphill plus 4 miles per hour is equal to the rate at which she can run uphill. So I'm just using R for rate, and I'm using U for uphill, and nothing for downhill at this point. All right, and again, if you want to use different nomenclature and variables and those type of thing, that's totally fine. But this is just a way that you can use this piece of information. Now, if this was a 5-point question, I think this is worth 2 points right here, to be honest, to just go and include these rates. Okay, and so now we have to go and figure out her rate of jogging each way. I don't have really anything for time, so let's just use t. All right, we can go and we can plug variables. T is just t. There's nothing you can do about it in this particular situation. If Rosa had like a head start on herself, maybe you could go and include that a little bit. But at this point, we're just going and we're listing this out. And if you're writing in pencil, erase, just go and edit and that type of thing as you're going through. Now, the reason that this is important is that now I can go and I can start looking at, well, how does one thing relate to another? Well, time is the same in both of these circumstances. So if you have something that's exactly the same in a column, great. Because what that allows me to do is just think about, how do I set things equal to each other? If I just divide both sides by r here in this given situation, and I say that d over r is equal to t, right? The reason I'm going to do this is that what I can do with d over r is that if I say distance 1 over r1, and if both people are both Rosas, whether it's running uphill, the distance running uphill over the rate of running uphill, this has to be equal to the distance of running downhill over the rate of running downhill. Okay, and so we can go and start plugging some of these in and looking at Rosa jogging downhill or jogging uphill. And so distance uphill. So now let's go here, and I can see that this information here is of some value. So distance over rate gives me time. And what I'm going to say is that if I go the distance uphill over the rate uphill, that's what I have here. And I realize I should use capital R's here since I had capital R's in my given table here. And so what I'm going to do now is I'm going to say that if she can travel uphill 3 miles at a rate of RU, okay, that's just a given piece of information that we have, and we want to be able to set this equal to something else. And you can see that this is just this information right here set into equation of time, just a quick little manipulation, since the amount of time that she has to be traveling for both of these has to be exactly the same. Okay, you want to find two pieces of information. You're hopefully having some constants. You're hopefully having something that you can tweak so that only one variable exists in that column, and then you're hoping that something's the same. All right, and so now what we're going to do is we're going to go and say that her rate downhill is 5 miles, but instead of saying RD is equal to the RU plus 4 miles per hour. And so now what we're going to do is we're going to cross multiply, and we're going to figure this out. So multiply, we'll get 3 miles times RU plus 4 miles per hour. And then we'll have this equal to RU times 5 miles. We'll get 3 miles times RU plus 12 miles squared per hour. No, the units are kind of working out weird here. That's okay. This is going to work out, trust me. And so, and the reason I know it's going to work out is now that I divide both, I want to figure out what RU is. So what I'm going to do actually is I'm going to subtract 3 miles RU minus 3 miles RU. Okay, all the units are the same. So what this is going to give me is 12 miles squared over hours equals RU over 2 miles. I'm going to divide both sides by 2 miles. The miles will cancel. That'll reduce this to a 6. Those will all cancel. And RU, so the rate running uphill, will equal 6 miles per hour. Okay, that's the RU there. And then if you want to figure out RD, we can plug that back into the original equation and say the 6 miles per hour plus the 4 miles per hour. All the units are the same. So RD is equal to 10 miles per hour. Okay, and so you understand that the distance between these two extremes has to be as such. So again, a way to kind of write it out into a table and then label some of that out. So let's look at this gardening example. So suppose Liz can weed a garden twice as fast as her friend Phoebe. Together they can weed the garden in 3 hours. How long would it take for each of them working alone? So we obviously have some basic comparisons that we're doing here. You know, we want to see how Liz and Phoebe compare. And with this is great information. This is what we want to find in the end game. But one of the things that I'm also going to need to do is how they work in a combined fashion here in terms of that. This isn't a variable that I can necessarily introduce. It's just, hey, how do they do things together? And so in terms of this specific question, this is the comparison that's going to be occurring. And then I think what I'm going to do here is I want to know how long it's going to take them. This is going to be one of my variables, all right, that I'm going to need to find. And I can plug something in here for now. So for example, if Liz can garden twice as fast as her friend Phoebe, what I could do is just say H for the number of hours that it's going to take her, and Phoebe's going to take twice as long because she's slower. She's twice as slow. We're just applying that in a little bit of backwards format, but we do know that in the combined sense, 3 hours of them working together completes the whole process. And so I think the second thing I'm going to do here is I'm going to try to set this up as a rate equation here. And what I'm going to do here is I'm going to say percentage of which they can complete per hour. because if I can find a percentage per hour, then I can very easily extrapolate that back and find some information here. And so I don't really have a whole lot for here yet, but I do know that I can get through 100% of the garden if they are both working in a total amount of 3 hours of time. All right, and again, part of the reason I encourage you to write the tables down, think about what you know, think about what you're looking for. You know, even if you're writing this stuff, I mean, I still think, again, with a 5-point question, this is at least 1 to 2 of the points here. This is at least 1 to 2 of the points here. And so now it's thinking about, how do I compare the other things? Well, I do know that a percentage divided by the number of hours it would take them is their rate, right? So I could say that Liz can complete 100% divided by the total amount of time it takes her. That's her rate, right? And Phoebe's the same way. So 100% divided by 2h. And we can just keep it as that. I know you could simplify that to 50% per amount of h time, and I'm not necessarily as concerned about that. And so, you know, we can just plug all this in for now. And so now that we have some of this, we can start looking at, you know, how do we, you know, compare this and plug this in and those type of things. And so what we really need to do is figure out, you know, what it is that we need to find. What are the variables in which we're trying to locate here in terms of this particular circumstance? Well, we need to figure out the rate at which they're working. We know the total amount of time it takes them, you know, combined like this, you know, but we need to be able to find these individual rates, so to speak. And so what we're going to do is we're going to go and say, for example, with the rates, you know, we can say that Liz's rate of 100% plus Phoebe's rate is equal to the total rate. All right. And some of you may be looking at this and like, oh, I know the answer. And if you want to go and just simplify these rates out, I'm not entirely opposed to that, but I am looking for, you know, a step of work. I want to know you can set up these equations however you choose to solve this. And again, I'm not trying to advocate that this is the only way to solve it, but this is how I'm going to solve this particular situation. Sometimes it takes a little creativity and intuitiveness to go and figure some of this out. But if I set up a situation like this, part of the reason that we're solving this with rational expressions is I'm going to use the least common denominator method. I see the least common denominator between these terms is 6h. So the least common denominator is equal to 6h, or least common multiple, whichever you want to use. And now we can just go and multiply everything by 6h and try to get it cleared up a little bit. So what that'll do is that'll cancel out the denominator. And so 6h, the h will cancel out. So we'll get 600. And then plus, if we multiply this by 6h, the 2 and the h will cancel out, because if you think about it, this is 2 times 3 times h. And so this will leave the 3 left, so this will be 300. And then we'll go, the 3 will cancel out, but then the 2 and the h will be multiplied together. So this will be 200h. All right, and then what's nice about this particular circumstance, you know, again, the idea here is that we just go and multiply the whole thing by the least common denominator, or least common factor here, and just this 6h just gets distributed to all the terms. Whatever you do to one side of the equation, you have to do to the other. So then we get this 900 is equal to 200h, and we can go and find that h is equal to 4.5. And in this specific situation, this is the the sweetness here is that we now know that it would take Phoebe 2 times h, so that would be 9.0. So it would take Phoebe 9 hours to do the gardening by herself, and it would take Liz 4.5 hours. And if we plug this directly in for h, we can go 100 divided by 4.5. We can go 100 divided by 4.5 and find that Liz can get 22.2% repeating completed per hour, and Phoebe would get 11.1 repeating percentage complete. And so a really slick and simple way to go about this process is, looking at these ratios and then figuring out, which column you're going to use. Now, one thing is that you could say h plus 2h equals 3 and then say h is equal to 1. That's not going to get you the right answer, and that should trigger a red flag, because if Liz can get it done in an hour and Phoebe can get it done in 2 hours, well, how does that work when it comes to them working combined to get a 3? So you have to use a little intuition. You have to understand that it's going to take them longer when they do it separately than when they do it together in terms of that situation. But if you can, attribute everything to one variable and then solve for it, you can go and find this information. Now, one of the things that I want to point out as an example here is, let's say we go and we find this information, and now we want to say how long would it take if Liz showed up an hour after Phoebe started. Okay, so if we said, Liz and Phoebe, and the reason I bring this up is I haven't shown you an example where there is a variation in time. Okay, so if we have time again, and we have rate, we would need to do the same thing to get to this point. So if I, in terms of this given question, I almost have to ask you this in the sequence. But if there is a situation where it says, someone showed up an hour later, we understand that we still have the rate of 100 over 4.5 hours. And if we take rate times time, we should get completion, right? Let's say percent completion. And so with Liz's situation, we have the rates. We have 100 over 4.5. Phoebe, we have 100 over 9. And if we want to know kind of what's going on here, we can use h for time for Liz and h for time for Phoebe. But one of the things I want to point out is that the only thing you need to do is, if you want to, account for Liz showing up an hour after Phoebe started, then all you need to do is go h minus 1. And that's going to subtract that hour that Liz did not help out. And so here, in this situation, we'll go h minus 1 times 100 over 4.5. We'll go h times 100 over 9. And the combined rate for these two will be h minus 1 over 100 all over 4.5 plus Phoebe's rate, h, which is 100 over 9, will equal the 100%. And so all we really need to do here, all right, we know this is 22.2 approximately. So this is 22.2h minus 22.2 plus 11.1h is all equal to 100. And what will occur is we have to add that hour there for Phoebe, or for Liz, I mean, and we can find that we just add really the amount of extra work needed to be picked up from Liz slacking and divide both sides by 33.3. And now we can find the amount of time that it took for them to do it if Liz took a break for an hour. And what you'll find in this situation is that this took 3.67 hours, or 3 2/3 hours, with that little bit of a break taken. So hopefully with this video you got a chance to see some different examples about how to look at some of these real world examples, how to set up some tables and just get some information jotted down just as a way to show your work and to navigate through this process of writing down rational equations to go and solve real world circumstances. And with that said, let's do some math.